Good day to all from wherever you are. My name is Ronnie from the Radio Navigation Lab in the University of Texas at Austin. On behalf of my colleagues Peter and Lakshay and my advisor Dr. Humphreys, I'll be presenting our proposal for securing terrestrial radio navigation systems, in short, trains. To start off, we all know that GNSS have provided excellent positioning solutions in open outdoor environments, shown by the shaded blue area in the picture. But there is an important gap in the deep urban and indoor areas where it is challenging to use GNSS. This is where commercial train systems such as Locata and NextNav have emerged to cover this availability gap in positioning. The architecture and accuracy of trains have been widely investigated. However, the security of trains parallels that of GNSS, and it will face the following vulnerabilities. First, if train is an open signal with open ICD, any users who have this knowledge can process its signals. Second, with open source GNSS signal generation software available online, as well as small and cheap RF hardware, the barrier to generate a valid train spoofing signal is not that high. Our lab is the first to come up with a concrete proposal on securing trains. To tackle the first problem, we have a navigation message encryption scheme, in short, MME. Our NME scheme will not only stop stowaways from riding the trains for free, but also offer those who pay more to enjoy better service on these trains. This encryption scheme have a block cipher running in the counter mode, which is one of the standard mode of operation for encryption. A key contribution we made is to add the encryption bit mask, in short EBM, to this scheme, which will offer multi-level encryption. This has not been used before in PNT security, and we believe that commercial trains provider will be enticed to adopt this, so as to offer different tiers of service. It might appear that the proposed NME scheme can also prevent an unauthorized transmitter from generating a valid signal. This is not true, as a spoofer might secretly be one of the highest tier subscriber and has all the necessary ingredients to generate a valid train spoofing signal in real time. To tackle this, we have a combined data and signal authentication scheme to aid a subscriber in having assured PNT. We look at the products of a vibrant research effort on GNSS authentication and chance upon this clever scheme that is already implemented on Galileo, called time-efficient stream loss tolerant authentication, or TESLA in short. This scheme enables the use of low overhead symmetric cryptography while achieving asymmetry via delayed disclosure of keys. Even with the authentication scheme in place, there are still two ways to spoof train signal, namely security code estimation and replay, in short SCARE, and half-duplex spoofing. As there is no defense for unidirectional communication against SCARE attack, we tackle the lesser problem of half-duplex spoofing. The MAC and key from TESLA are usually packaged together at the end of an epoch. During this interval, a half-duplex spoofer does not have the prior knowledge of the TESLA MAC and key to generate a valid train signal. However, it can choose to modulate its transmission amplitude to leave an open window for the true signal to pass through. Here is what a potential half-duplex spoofer will do. At the start of the predictable portion in yellow, it can slowly increase the offset. But this offset has to be throttled down before the start of the unpredictable portion in red in order to avoid sudden jumps in position or velocity, which can be detected by the victim receiver. To tackle this, we came out with a BackLeveling scheme. The idea is similar to leavening in bread, where bacteria and yeast form a small bit of leaven spread throughout the new dough in the pre-baking process. In our case, the leftover MAC bits after truncation, like the bacteria and yeast, will spread throughout the whole set of data packets by interleaving and convolutional encoding. With BackLeveling, we increase the number of open windows of unpredictability, shown in red. This means that the spoofer has to keep transitioning the offset back to 0 before the start of each unpredictable interval in order to avoid detection. This will definitely limit the adversary effort to spoof large position offset. In summary, we draw upon the flexibility offered by a clean slate trains waveform to derive the first public proposal in securing trains, in which two designs are novel. First, we have a selective NME scheme which not only prevents unauthorized access, but also provides tiered subscription service. Second, we added a BackLeveling design into the original TESLA protocol so as to minimize the impact from half-duplex spoofing. Our proposal presented today is our first foray into improving the security of trains, and we will continue to work towards our goal of providing trains with a comprehensive defense against spoofing. With this, I welcome any questions from the audience.